All right. So today we are going to be totally switching gears from SQL and talking about sorting algorithms. We're going to warm up with the bubble sort we know and love. We're going to work on insertion sort as sort of a variation. But then the big meat and potatoes of today's lesson is merge sort, which is an example of a divide and conquer algorithm. Which in fact has a much better runtime complexity. It has its big O is n log n. And can someone remind me what the big O of bubble sort is here?
N squared, if I remember correctly.
Yep, big O of n squared. And give me one sec here, folks. I have my audio coming through speakers instead of headphones, which is not the end of the world, but is a little disconcerting. Okay, there we go. Can I get a quick mic check, please?
Hey, Adam.
Perfect. Thank you. So we're going to look at insertion sort. It's going to be similar to bubble sort. Merge sort, again, is going to be a wholly different beast. So the goals for today, first of all, is learn insertion sort, learn merge sort, but it's not just about learning these algorithms. We also want to be able to think about how the data impacts runtime performance. What sort of input produces worst case performance? What sort of input produces best case performance? What sort of input produces average case performance? Which one of these three do we normally care about when we're talking about algorithms?
Worst case.
Yeah, worst case. And worst case is what big O is, right? Big O is our worst case performance. And why do we care in particular about worst case performance? So the answer to this is a little more subtle. Um, as you have been discovering, like software development is in some ways, it's very much an art as much as a science. Really, engineers love, not just software engineers, love estimates, right? And worst case performance is our worst case estimate. So if I can design an algorithm that performs reasonably well in a worst case scenario, then I know it's going to do even better for the average case or worst case. Um, and we'll see about like what different inputs produce best, average, and worst case runtimes. But once our programs are out in the wild, so to speak, we don't always have control over that, right? And so if we just use worst case as our baseline, we're guaranteed that this is the performance our algorithm will get. So those are some of the reasons why, like in general, worst case performance is usually what we look at. And I think what's really important as we get into this, it's not just about, it is important to understand how the algorithms work and be able to identify big O, but also just being able to think about this and talk about this. Um, and so in that vein, before we even like write code, let's put in a little bit of data. And let's say we have a list that looks like this, and everyone can read the font size and stuff, and everyone's good to go. Awesome. And bear with me just a moment here. Gonna make our little objects that we'll be using for a while here. We have 4, we have 3, we have 2, we have 1, and in fact, I don't need that one. And let's throw these in our list. And let's get ourselves a nice big fat arrow. That's going to be our pointer. So someone described to me in plain English, how does bubble sort work?
It takes um for every for every sequential pair of elements within an array, it compares them and orders them so that the greater of the two elements is in front of the other element. And it repeats this until the entire list is ordered sequentially in non-descending order. Or I guess according to whatever criteria, it doesn't have to be in like that order specifically.
Yeah. Now, how does bubble sort make sure that, like, does it use a while loop? Does it use a for loop? How does it?
It uses a for loop.
Nested. Oh crap.
Yeah. And it in fact has nested for loops. Yeah, but this is a pretty
Hello,
good
this is
breakdown,
Decimal.
right? And if we were looking at the behavior of bubble sort and we
Hey,
were
Justin,
mapping
you're
through
hot
this.
miking.
No.
Oh, thank you.
Sweet.
One sec here.
I got you.
Oh, yep, you beat me to it. Thank you. So basically, right, if this is my pointer for bubble sort, it's over here. It compares 4 to what, the next one, the one after. And if they're not the same, then it swaps them. And then it moves on. And if 4 2 are not the same, it swaps them. And if these are not the same, it swaps them. Right. And then if these are not the same, it swaps them. And now it doesn't And now we're going to do that again, right? As we go through here, and you guys can see how this go, where 3 and 2 would get swapped, 2 and 1 would get swapped, and so on. We'll do this manually as we get into other algorithms. There's actually a great site called PyAlgoviz that we're going to take a look at right now that has this visualization for us. And let's get a little more screen real estate here.
That's a really cool website.
Yes, it's an awesome website. It has all sorts of algorithms, not just bubble sort. Um, I haven't gotten fancy enough, but you can like customize the Python visualization code as well. I forget what Python library it's using, but a really popular one for visualization. So we can, in fact, modify all of this. Somewhere in here, I believe they've created, it looks like a list of 30 is a lot. Let's just stick with maybe, well, we'll leave 30 what they have. They've created a list here, it looks like in increasing order of 30 items. And bubble sort, there's a couple different ways to implement it, but it's relatively straightforward. If we look at what's happening here in the code, we have two nested loops. What we see is that the outer loop is taking us through everything, but then the inner loop gets applied. So in fact, this is where the n squared comes from, where this inner loop is going to go through our entire list of length n times. But since we do it for every single element, it's n times n, and we get a worst case performance of n squared. And here we see they're doing a comparison for list item J if it's greater than list item J plus one. And if it is, I don't particularly like the way they do the dual assignment here, but I'll leave it. If it is, they are setting list item J to be equal to J plus one, and then list item J plus one to be equal to J. So this is where the swap happens. But let's run this. Yeah, 30 is a lot. Let's work with 16. So that was a bit quick. Let's run through this manually and see what happens. And this is, you could do this with the debugger in VS Code too. I just really like this visualization. So here now we're starting our loop. Um, let's see here. It looks like something got a little off. Yeah, I think I'm going to set this back to 30 because I think, my apologies, I didn't think that fiddling with this would cause an issue, but the visualization seems like it's gotten a little off. So now if we run this at molasses speed, let's see how we do. There we go. This looks much nicer. Here we go. So we can see they actually have our outer loop starting at the end. And what they're doing, in fact, is comparing from the beginning against the last element. Um, and we can see this swapping happening along the way. And we can see that this is pretty slow. Let's maybe go from molasses to snail. But we can see here the bubbling that people talk about in the name. And we can see here the outer loop has now been reduced, right? Because what we've guaranteed now is that the biggest thing is at the end. We can see that, in fact, what's happening is we're bubbling the biggest elements forward. And we can also see why this is a big O of n squared algorithm, because in our worst case scenario, the biggest element is all the way, it's in backwards order, right? And we have to flip everything around. So I'm just going to let this run, and I just want to pause and see if folks have any questions. And is it useful to see this visualization too? And kind of, I know you guys have seen bubble sort too, but to sort of like talk through it this way. Awesome. So it's actually doing pretty good here. We can kind of see it run along. We can do the same thing in TL draw. And I do recommend like doing it that way when you're designing algorithms, is like using a piece of paper. And we will with insertion sort. But I figured this is such a nice visualization to see that this is a good place to start. Andy, yes, sir.
Um, for junior developers, is this something that they would go through first, like the bubble sort? I feel like this comes intuitively because you're trying to compare the nearest two values, and then you just go do it over and over and over again. Like if somebody gave me this challenge, that's kind of how I'd approach it. Is this like the lowest level type that you would algorithm that you would use, or the
Yeah.
slower, most worst performance?
You mean in terms of like an interview or like a real world scenario?
Yeah, interview probably, yeah.
Yeah, they might give it to you in an interview. Um, it depends on the company. Some places do more algorithm stuff. If you're going to Google or someone like that, they're definitely not going to give you this. They're going to give you more advanced stuff. Often they might not even ask you to implement, frankly, a search algorithm in a leak code problem. Sometimes the leak code problem, the way the problem is designed, it encourages a certain algorithm. Um, Even with bubble sort, though, I do want to point out there are tricky bits just to remember. Like I had forgotten that the outer loop needs to start at the end and work backwards, right? And that's how we guarantee that we're getting the biggest item to the end, and why we don't need an infinite while loop, why we can have the two nested for loops. Um, Also, I think one of the most common gotchas, even with the simpler algorithms, is pointer manipulation, right? And if we find that two elements are out of order, we want to swap them. But what's the problem of if instead of having it in this existing order where we set j equal to j plus 1, and then we set, well, in fact, now I've broken it by doing it this way, because if I set j equal to j plus 1 and I set j plus 1 equal to j, like
You
if
need
we
to include
have,
like a temporary variable, right?
yeah, exactly.
You could, can you do
Do it all in one line.
LJ, yeah, comma, LJ plus one is equal to LJ,
That's,
comma, LJ plus one, and do like an interpolation to flop it?
they did it here all on one line
Yeah.
like this. Um, I actually don't recommend this. You almost never do this when you're actually coding. It's considered a bit of an anti-pattern because frankly, it's really easy to have typos in there. Maybe it's okay here, but you won't see it a lot. And if you don't do it this way, then indeed you need a temp variable, right? Because you if I don't have a temp variable and I'm swapping, 5 and 4, well, over here, L of j is now 4. L of j plus 1 was already 4. And so when I set L of j plus 1 to L of j, it's 4, and we've lost 5, right? So I need some sort of temp variable to hold that value. And then I can say, L of j equals L of j plus 1, and L of j equals temp. So like pointer manipulation logic like this, to go back to your question, Andy, Lloyd, when you're doing it live on the spot, whether it's for this specific problem or a different kind of one, is a real common gotcha, and it shows up all the time in LeetCode problems. So often, like that might be part of what interviewers are looking at. Yeah, great question. Other thoughts or questions around bubble sort before we take a look at insertion sort? Okay. So the one thing I do want to point out with bubble sort before we move on, and let me kind of undo all this. I think that takes us back to where we were. So if we run this at a snail pace, let's see here. Let's run it. I want to run it with some slightly different data. Let's try data. Let's see if this works. 3, 2, 3, 4, 1, 5, 6, 11, 50, 55. So let's see if this works, if I can get this to run and look good.
So I think that the visualization Python script on the bottom, line 12, you see 30 in there. If you change that to the range you want, that might change it.
Yes, great call. That is almost definitely what's going on here. Let's see. Yeah, we'll see if it messes with the rectangle size or not. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think I have 9 things. Let's see if that works. Yeah, it's unfortunate because it looks like it's also
The width of the bars.
yeah, the width of the bars and all these things. It's a little brittle. What I wanted to point out, and it's going to be hard to see it exactly. I'm going to change this back to 30 because I'm not exactly sure what this is doing. But that is a good thought. And actually, I will fiddle around with this later to get this working. If we look at this data here, there's only one thing out of place, which is item 1, right? However, the algorithm is going to keep running all the way through both loops. We don't have a stopping point. So as I run this algorithm through, ignoring the fact that the visualization is totally off, note that now the algorithm's sorted, but the algorithm doesn't know that, right? And it just keeps going. And this is a lot of wasted steps, right? So bubble sort doesn't actually know that it's done when it's done. You can actually modify bubble sort. You probably wouldn't do it because it's not worth the effort because you would just use a better algorithm. But we could introduce a variable called swapped. And we can keep track of when we swap two elements. Right. And so what this does is we start out with swapped equals false, but then when we find something out of place, we set swapped to true. And every time we go through the outer loop, we do the same thing. So if we go through an entire loop without swapping anything, swapped remains false. And we tell our program to stop running. And I don't know exactly where the print statement will show up, if it shows up at all. But we can modify bubble sort. Now, this doesn't matter for worst case performance, right? But for average case or best case, it will improve this a bit. I don't know if we'll see a print statement happen, but what we should see happen is this algorithm should actually stop running. And in fact, we then see done and program finished. And we see here our pointers are where they still are when we completed this loop once without swapping anything. So we didn't do all of that extra work. And I just want to check in to see if folks have questions around the mechanics of how this swapped Boolean is working with bubble sort. Cool. Andy, yes, sir.
Uh, I might have missed it, but I was just wondering on the order of reassigning the J's. I'm a little confused. I think you maybe went over it, but I was wondering if J equals to J plus one, then J plus one equals to J that doesn't really change anything, does it? If it goes in order.
If they're already in order, you mean?
So I mean if J equals to J plus one initially,
Mhm.
in that conditional statement, and then you're doing J plus one equals to J. Well, and when it gets to J plus one, J is also J plus one.
I see what you're saying. Um, you know, I hadn't thought about it until I broke this down, but I think when you put it all on one line like this, Python must be creating like a temporary variable that in effect does both of these operations. They can't actually happen both at once, right? But because you're correct, otherwise this would do nothing. So under the hood, Python must be creating a temporary variable here. And in fact, if we ask ChatGPT, does Python create a temp variable for multiple bar assignments on the same line, such as, yeah, I guess it creates a tuple. Because you're absolutely correct. Otherwise, they would be set to the same thing.
So the
And we would need a
syntax
temp variable.
matters here in that case.
Yeah, it absolutely does. In fact, the way I would write it is I would create a temp variable and I would not do all that stuff on one line. I would just use my temp variable. I think that's actually a cleaner way to do it. This is a great example of like after graduation, you should pick a language and really master it. And mastery means like I did not know this, like that Python creates a temporary tuple to handle multiple variable assignments, right? Like digging in really at this level of the language. Um, Great question. Circling back to this swapping example, the reason I wanted to point this out is not so much about implementing swap, though it is kind of nice to see. And it's good to realize that bubble sort doesn't know when it's done. It'll just keep going. But to point out how this only matters for certain kinds of data, right? If my data is really bad, in the worst possible order, we still hit our worst case performance. But this modification improves best case performance, big O of n, not strictly true. We're still looping through a bunch of times, right? But I just wanted to use this as an example to show how the shape of the data impacts our algorithm's performance. Do folks have any questions or stuff they're curious about before we switch gears and take a look at insertion sort? Okay, cool. So insertion sort is very similar to bubble sort. We're going to loop through the array or the list left to right. We're going to examine each item and compare its to its neighbor. And this is the difference. When a smaller left neighbor is found, insert it at the correct position in the array. And let me go ahead and let's write out an implementation and then we'll play through it with TL draw. And I know we're in Python, but it's just easy to call stuff an array. So we still end up needing a nested loop to implement this. So this is our outer loop. And we still need an inner loop. And we're going to compare left, right items. If left is bigger, shift right. So we're comparing really very similar to with bubble sort. These two items and let's do J and I because J is on the left. If J is bigger, shift J right. And then we're going to decrement J and keep comparing backwards and shifting until item J is smaller. So we do our comparison here. And we also, so we compare and loop. And here we're going to bubble J back. And here we're going to set up to compare J to the previous item. Once we exit the while loop, we know that item is bigger than item J. So we insert item. Sorry, I believe that should be to the right. Item J, and everything in the list up to index J plus 1 is now sorted. So let's grab this. Let's make this a bit bigger. And let me make a couple extra items. Let's see here. 3, 2, 1, 4, 5, 9, about 6, 7. And let's get rid of this stuff here. And we need a couple pointers here, actually. And let's make this one red. And this will be I. And this will be J. So if I have this implementation right, we start off and let's also have, something to represent our item. Um, as we go through this line by line, we start off with, we build our loop. Our item is at the beginning of the loop here. So item is 3. And we actually set J to, sorry, item, my apologies, starts at index 1. And in fact, let me add our indices here. There we go. So now I think I have this correct where I is at index 1. And J is at index 0. And while J is greater than 0 and the value of item is less than array sub J. So if we look at the value of item, it's and in fact, let's see if we can't rotate this. Yeah, I'm not sure why that's not working, but we'll put them both here because I think this will actually be easier to see. So the value of item is 2 and the value of J is 3. So indeed, item is less than array sub J. So what we're going to do is we set the value of J plus 1 to equal to BJ. We move 3 up here. And let's put item over here so we can help keep track of stuff. So we move 3 forward. And we move our counter back, which it looks like I actually may have an issue in the code here. I apologize because this would move J to be -1, which is definitely not what we want. So let me see if I can fix that real quick.
It's the same in the pi algo viz. It shows the same way that you did here.
Got it.
think because your while loop has that condition where J has to be greater than or equal to 0, it's okay for J to go -1 or negative sometimes, because then you
Oh,
just
of
won't run the
course.
while loop.
Of course. Yeah, thank you so much. So I'm totally getting lost in the sauce here. I apologize. Yeah, let's see here. I want to make sure I get this right. I may be getting something wrong here. I actually am going to pull up PyAlgoviz because I'm getting lost in the sauce, which isn't going to do us any good. So this is extremely similar. Um, let's see what happens as they run this, and let's see where I was getting confused. So it looks like,
In the while loop, where the well, actually it's the same thing though. It wouldn't really matter. You just reversed it.
yeah, so while J is greater than 0 and the item is greater than they say val instead of temp, um, J,
The S of J must not have been greater than val because it skipped the while loop, right?
right.
S of J is 0 is greater than value, where value is S of I. Yeah. Uh, 0 is not greater than 1, so it skips the while loop, and J never actually goes negative here,
Got it. Let's see.
right?
I think so.
S of J would be 0. Wait, no, that's the index.
Yeah, so S of J, so J's at 0, which gives us the value of 24. I see a hand up, just a minute. I want to make sure I don't get totally, I'm already lost in the sauce a bit here. So S of J when J is 0 is 24. Value is I and I is 1. So that's 30. So they're checking that things are out of order, right?
Yeah, and they're not in this first case, so it just skips the while loop, this first iteration, because 24 is not greater than 30. So it says, oh, we're not going to do the while loop. Let's move on.
Right. I'm curious. Let's change this around. Let's have the first one be bigger than the second, because this is where I was losing my mind a bit here. And let's stop this and pull it back to the beginning. So I is 1, J is 0. So now the value of S of J should be 30.
So yeah,
And val is S of I where I is 1, so that should be 24. So now we should enter into the while loop. And indeed we do. And so they set S of j plus 1 to 30. So they're going to swap the values. Yep. J equals j minus 1. So this is where I was losing my mind because I feel like this is going to make j negative. And indeed it does. But
And
we're
so
kicked
it's not going to run the while loop again
right.
since J breaks that condition of being greater than or equal to 0, and just going to set the value in line 8,
Right.
I think.
And it sets. So I see. Okay, j plus 1 is 0 now. I
And
see.
it sets
So
it to the old value.
yep. I apologize, guys. This is where I was totally losing my mind and not keeping track of what was going on. J is -1, but guess what? We don't care because that's as low as it's going to get, and we add 1, and that brings it to 0, and that sets it to the old value. So that works totally correctly. So I apologize. I got completely lost in the sauce here. This is a great example, though, of how, frankly, doing this stuff live is tricky. And also, for better or for worse, why people these are still viewed as useful and technical interviews. So I have mixed feelings about that. Um, and thank you guys for being patient with me here. So J indeed does go to -1, but then we increment it back up to 1 to 0, which is fine. And then we set our last element to be value. And then we see that happen right here. And now I moves on to 2. J gets reset to I minus 1. So now we're back and we're good to go. And we can see this same pattern happen. And we see with this while loop, J keeps moving backwards. And so, as you guys just saw, this is the difference between bubble sort and insertion sort. While they both have like worst case runtimes of n squared, insertion sort will have the entire list sorted as we build it up, which is kind of nice. Right? And now I'm guaranteed that everything before I is sorted. And we can see this happen again. And again, everything before our red bar here is sorted as we build this up. And we can just kind of keep watching this happen. And I won't go through the whole thing, but I'll just do like 1 or 2 more. Or actually, I'll run it at molasses speed. And we can watch it and I can take questions. And Andy, I think you had a question.
No, I was just going to recommend to go through the visual of how the code works and just look at the J because that made me understand the J equals J minus 1 thing.
Yep.
Yeah.
Yep. No, that's a good call. And it was staring me right in the face and I just couldn't see it. Right. And so thank you guys for your help. And if there's a meta lesson here, it's sometimes if you're stuck, you got to find another way to look at the problem. Why don't we break? Why don't we take 5 if that's good for everyone? And then we'll come back and we'll look at merge sort. Sound good? Do we want to do 5 or 10?
I say 5.
Yeah, let's do 5. All right, folks, thank you very much. And in 5 minutes, we'll take a look at merge sort. All right. So, we looked at bubble sort, we looked at insertion sort, and this lesson, by the way, is under, we have a sort of data structures and module here at the end here. There is actually a better diagram of what I was trying to accomplish with the different insertion sort example here. If folks want to peruse it later. The insertion sort code is there in our lesson as well. and really everything we've been talking through. There's a little more detail on insertion sort. There's a complexity analysis both for worst and best case performance. We didn't get really time to talk about it, but you guys saw how because insertion sort sorts the whole array as it goes, if you have a list that is partially sorted, like if we look at this list over here, where the first half of it almost is sorted, insertion sort will perform better than bubble sort in this case. And an almost sorted list is called a k-sorted list. And there's a bit of a breakdown of this as well. I think the important thing is we saw insertion sorting as we go. And we also saw just how tricky this stuff is to do live, where the code was correct, but because I got thrown off by, it's not an edge case, right? Because our code didn't break. But when you're doing insertion sort, and the second item is bigger than is smaller than the first and needs to be swapped, our J counter goes to -1, which is a little bit of a weird behavior, right? But it actually works out just fine. So that's kind of why these things stick around and why just practice and people talk about grinding leak code before going into interviews, and that's why. Because I could be writing a full stack app all day, but it's not going to help me on a leak code problem. It's different skill sets. Let's take a look at merge sort. So merge sort is a divide and conquer algorithm. We are not going to use nested loops. We'll eventually implement this recursively. Today, we'll implement it iteratively, so we can really appreciate the clean, elegant, recursive approach when we get there. But before we implement the code, let's look at the logic of how this works. And every single divide and conquer algorithm takes the same approach, right? Divide and conquer is all about taking a problem and let me in fact let's put it in our notes. Divide and conquer is always about the same things. Divide a problem into subproblems. That are instances of the same problem. The subproblems are the same kind of problem, they're just smaller. Conquer or solve the subproblems by solving them individually. Oh, sorry. And then combine the subproblem solutions to get the solution for the original problem. And that's what binary search does, right? And log n, you almost always see in divide and conquer problems because log n is log n of base 2 of how many powers of 2 do we need to solve this. And when you're dividing a problem, we often divide it in half. And so we're turning one thing into two. And in fact, we'll see that in action here in a moment. And I just want to pause and check in and see if folks have any questions thus far. All right, let's visualize merge sort and then we'll implement. So that's going to be too thick. Let's divide our one big unsorted list into 2 smaller lists. And give me a moment here just to get rid of the things we don't want. Right? We have a smaller list here. And we have a smaller list here. We've divided our problem. But we're not done dividing. Our problem isn't simple enough yet. We want to keep dividing until our problem is absurdly simple. So let's divide in half again. And we'll grab these two and we'll put them over here. And we'll grab these and they're going to go, oh, that's good enough for me. And those will go over here. So our problem is getting even simpler. And we have to do the same thing over here. So please do bear with me for just a moment. I think that looks about right. And now our problem is getting a whole lot simpler. Let's kind of pull these all down a bit. But this isn't quite simple enough. I want to make it even simpler. And in fact, at this point, let's just get rid of that because now our simplest problem is simply a single value. And I'll do a little drawing here to visualize the dividing. But let's also do a little drawing here to help us keep track of what's going on. Because now that we've divided, we now need to conquer. And the other thing I want to point out before we start the conquering is we divided three times. Right? We divided the first time, we divided the second time, we divided the third time. And I also want to point out, we had a list of length 8. And log of 8 base 2 is 3, right? Because 2 to the third power, 2 times 2 gives us, I don't know why it's doing that. I apologize. 2 times 2 times 2, 2 times 2 is 4, times 2 again gives us 8. So this is where this log n in n log n comes into the big O of our algorithm of the runtime, the worst case runtime complexity for dividing and conquering here. Now, we have all these nice little lists. We have like 8. Right? So here n equals 8. And now we're going to run through all of them to sort them. And so what I'm actually going to do is recombine everything together, but in a sorted way. So comparing a number to itself is easy. So let's look at these two and let's combine them. Now, luckily, they're already in a good order. Let me put this off to the side. So these guys can stay where they are. But 5 and 4 are not in a good order. So when we compare them, when we combine them, we swap them. And note how this is really easy because we only have 2 items to compare. And if I look at 9 and 4, I see the same thing, where when we combine them, we need to swap their positions. And if I look at 1 and 7, well, these guys are in the right spots, so they can stay as they are. Right? So we divided. Now we're starting to conquer. I'm not going to draw all the green arrows because that's a lot of arrows. And as you can guess, we're now going to do the same conquering here for these guys that we've just been working with. So, and this comparison again is really easy because all I need to do is go through both of these lists and compare the first item to the second item. And 2 is less than 4, so it goes in first. Let's move this counter forward. 8 is bigger than 4, so we're not going to put in 8, we're going to put in 4. And now I move this counter forward, And 5 is less than 8. So we're going to put in 5. And now we're at the end here, and 8's all that's left, and we can put it in. And this is a really nice, simple comparison, right? And in fact, our runtime for this is 2, right? Because that loop has a length of 2. So it's 2 plus 2. But because there's not multiplication, we don't care about that. So we can say big O of 2. And 2 happens to be, oh, what is it, like n over. It's probably, in fact, something. I'm not sure how to. I'm not sure how to write it correctly. I think it would be this. But my brain is failing me at the moment, so I'm not going to worry about getting it the right way. I'll add that later. But we see here that we're doing basically 2 comparisons. And then over here, we do 2 comparisons again, because we repeat this same process, right? And let's get rid of these guys. I compare 4 and 1, and lo and behold, 1 is the bigger number. So 1 goes in, and we move our counter forward. I compare 4 and 7. Lo and behold, 4 is the bigger number. And we move this counter forward. I compare 9 and 7, and lo and behold, 7's bigger, and then we're only left with 9. And 9 goes on in. And as you all can probably guess, we're going to do this one more time. And do our final comparison. And guess what? When we do this, we're going to be doing 4 comparisons, right? Because I've got 4 things, and I'm going through this list once. And I go through this list once, but they're not nested, so it's not 4 times 4. So it's essentially big O of 4. And I compare 2 to 1, right? 1's smaller, so 1's going to go in. We move this counter forward. I compare 2 to 4. 2's going in. We move the counter forward. We compare. The 4's are the same. Right? So like this counter is moved forward and the other ones move forward. 5 is less than 7. 7 is less than 8. And then we get to 9, and that's the end. And if I look at the number of comparison operations, I've got 2 plus 2 is 4, plus another 4 is 8, which happens to be n. So I've got n times log n is my runtime complexity here. And I think I may have not quite laid out the logic of where the n times the log n get multiplied together. I think the right way to say it is we end up doing really like 8 comparisons for each layer here, right? Because we still have to compare these. We're still going through the length of the whole list 3 times effectively. And I apologize because I think I'm doing a little bit of hand waving there and getting some of the mechanics of it wrong. But hopefully at sort of like the conceptual level, does it sort of click a bit while we're looking at a runtime complexity here of n times log n for this divide and conquer algorithm? And how are we feeling about the conceptual approach to merge sort and its runtime complexity? Are we feeling pretty good? Cool. And in fact, let me use ChatGPT to help fix my errors. Because this is where I was struggling a bit. And so again, I think we all really get the divide part. And we get the sort and merge part. And we get where the log n comes from in the dividing. And then the conquer step. And this is what I didn't quite explain right. At every level of, as they say, the recursion tree, because I think you guys can see how this is a great example for a recursive algorithm where it's happening in little chunks, but we're comparing every element in the list. We're essentially looping through the whole list just in chunks for every level of our dividing steps. So across each level, we do a loop through the whole list, which is big O of n work. So does that help break down the runtime complexity a bit more clearly here for merge sort and divide and conquer? Okay, awesome. Does this feel pretty intuitive now that we've kind of walked through it this way? I'll take that as a yes. And my guess is it does, especially since I know I went through it pretty exhaustively. But that's going to be good because as we write our code, that's where the complexity is going to come in, right? Now, again, I want to mention that this is really like a prime example of a recursive algorithm. You can see how, like, in effect, we're doing the same thing. So really, you want to write this recursively. Today I'm going to show it iteratively because then when both sort of for reps and sets with pointer manipulation and stuff, but also so then when we build it recursively, we'll appreciate how clean and elegant that is. So let me put this off to the side and we'll kind of just let that. We'll let this sit as a reminder here for what we're doing. And you all want to dive into write code or take a short break? Because I know I've been doing a lot of talking here.
Will
All
we
right.
have time since we got retro in 20 minutes?
Yeah, it is a little tight. Why don't we take a 2-minute break? How does that sound? Yeah, let's do that. Let's take 2. Just get up, stretch your legs, grab water, go to the bathroom, and then we will implement merge sort. And this will let our brains kind of just rest a bit too, which will be perfect. So thank you very much, everyone, and I'll see everyone in 2 minutes. So again, really the way to implement this is recursively. However, it is going to be really good learning to implement it iteratively. And we'll see later how to implement merge sort recursively. Like in an interview, you should implement merge sort recursively. That's going to be what they expect. Most divide and conquer algorithms are recursive because you can see the nature of a divide and conquer algorithm lends itself to recursion. Um, and a good challenge for today could be to try and figure out a recursive implementation on your own, which we will learn later. So we're going to have two functions, merge sort, which is going to be sort of our main or master function, and then it's going to call merge. And merge sort's job is going to be to do the dividing, right? And then also the combining. And merge's job is going to be to do the comparing of our sorted lists. Because as you'll note, just like insertion sort gives us a lot of sorting along the way, once we get to the comparison step, every single list we're dealing with that we're comparing is sorted. A list of one is sorted because it's only got one thing. And then when we compare these two lists of two elements, well, each of these little sublists are sorted. And that's what's going to make this nice and efficient. So I'm going to build out a lot of this merge sort logic, and then we'll implement the merge for the comparison because that one's a little more straightforward. So first off, I want to get the length of the number of stuff in my list. I'm going to use this a bunch, so I'm going to put it in a variable. Next, we're going to have a base case, if we were implementing this recursively, of sublist size is 1. There's no need to sort, right? If we've gotten to here, we don't need to call merge to do any sorting. So I'm going to check, and let me rename this to items length. If items length is less than or equal to 1, we can just return all of our items. I need something to help keep track of the size of the sublist I want to work with. So we're going to build our sublists bottom up. We're going to break each item in the list into its own sublist of length one, then combine them into sublists of length 2, and so on. So the implementation is not going to follow the conceptual approach of breaking this into 2 lists of 4 and then 2 lists of 2, 4 lists of 2. We're just going to break everything into a list of 1 because it's easier. So to help me do this, I need a variable that keeps track of how big each sublist should be. And we're going to start by breaking everything into sublists of 1. I am going to write a while loop here, but we know this while loop isn't going to go on forever. And we're going to say while sublist length is less than the total length of items in our list. Because if the length of our sublist ends up being the entire list, right? When we get to this step in conquering, that's when we know that we're done. So until then, we need to keep breaking stuff down into sublists. To do this, I am going to use a little bit of fancy Python. And full disclosure, I definitely looked this up to help get this working. We're going to use a range. And what this does, and it would help if I had the in, this chunks the entire list into sublists of length 2, 4, 8, and so on. So this range doesn't go through every single item. It starts with it basically starts and it will start with like 1 and 2 and 4 and so on. It chunks the list into smaller parts. And out of this, I'm going to grab my left sublist. And let me fix my syntax here. So we're slicing from the beginning of the list, or rather from our counter, and we're grabbing a sublist of the desired size, right? So at first, this will be a sublist of 1, starting at 0. Later on, it'll be a sublist of 2, like starting at 2 and 4, and so on. But we need to do something similar for our right sublist. And note that we start this slice further out, so that if this slice is starting at index 0, when we're doing sublists of, say, length 2, our right sublist will start here. And again, we need to push it out so that my left sublist is grabbing what's here on the left, and the right one is grabbing here on the right. And I'll fully admit it took me a bit to get these, like this slicing logic and this range logic working. The example code in the curriculum has a bit more explanation in the comments, as well as a couple links. And I think that will be a really good reference, but hopefully everyone's kind of tracking at a high level what's going on here. So this lets me loop and build up sublists, starting with sublist length of 1 and then 2 and so on. And once I have my sublists, I need to compare and merge them. So I need to compare, sort, and merge the sublists. And this is going to use the merge function that we haven't written yet. And finally, once our sublists are merged, once, say, I have this sublist right here, I need to put it back in at the right spot. So I'm kind of like comparing and sorting and then putting the sorted sublists in place, because we're continually slicing up this items array. So all of these comparison operations that you guys see happening here and here and here, because we're doing this in a for and a while loop, and actually starting by breaking it down into these chunks, like once I have these guys sorted correctly, I need to put them back in the main list at the right spot, and these guys here, so that when I do my next size chunk, it will pull from our pre-sorted list. So it's not quite in place, but it's sort of a similar concept. And again, once we see the recursive implementation, we'll see that it's a lot cleaner. And then finally, once all our sublists are sorted, build the next sized sublist. So our sublist length, we're going to double, right? Because the way that we're building this algorithm is we're going to start by breaking everything into lists of just one, which is trivial, but then we need to break it into lists of two. And that's when, as we do these little sorts, they go in place. And then we break stuff into lists of four. And if we had an even longer, if we had like 256 items, we would keep breaking them up. So we need to double our sublist length. Once all this is done, we are then going to return the list, which will have been basically sorted in place. Let me implement the merging function that compares two sorted lists, and then I'll pause for questions. And remember, the job of this function is when I have this sublist here of 2, 8 and 4, 5 to compare them. And the process is going to be by having these two counters that move through. And later on, when I have my bigger sublists, to compare those two as well. And since these guys are sorted, it's the same logic. So I'm going to make a result array, a result list to hold results to make life easier. I'm going to make some counters. And these are the little arrows for here and here, right, to compare the two lists. And now I'm going to use a while loop, which is not my favorite, but it actually makes sense for this sort of logic. So we're going to keep looping and comparing and incrementing our counters until our counters hit the end, right? Until I is length of j, or length of its list, or until j is length of its list. We're going to need to do a little extra work in a bit that we'll see, but this is sort of the main logic. And if our item on the left is less than our item on the right, then let's put it in our result list. If 2 is less than 4, let's put it here in the result list. And let's increment our left counter. But on the other hand, if the item on the right list is smaller, let's add that one to our result list. And let's increment that counter, right? Where we're comparing 8 to 4. Well, 4 is smaller, so it belongs next, and we increment the counter.
Would it be right J or is it right I?
Oh, it should be right J. Thank you so much. That's a typo. Now, there is a situation that we've run into here. And in fact, if we use this example here from the TL draw, we can see it. I now have both of my counters at the end of their lists, but there's still stuff I need to put in. I've put in 2 and I've put in 4, but I still need to do some work. So I need to check to see what's left in each of these lists and add it in. And in fact, I think we probably would have done one more comparison, in fact, with this logic, because we would have said, let's see, well, I
Yeah,
is less.
because I and J are both 1 right now, right?
Yeah.
And the length is 2, so the while loop still runs at least one more time because both of those are true. We haven't hit the break of the while loop.
Oh, right, because length is 2. Yeah, you're correct. We haven't hit the break of the while loop yet. So I is 1, J is 1, but the length of each of these lists are 2. And I is over here pointing at 8, and J is over here pointing at 5. And
We got to do one more iteration of the while loop to
yep. Yeah.
figure out which one is bigger.
Yeah. So thank you so much. So we continue looping through. We compare our left to right. We see that 8 is bigger than 5, right? So the one on the right is smaller. So we add in 5. And we increment our J counter. So now J is set to 2. And we hit to the top of the while loop. And now we break and exit because this is an and. And this is saying both of these need to be less than the length. But luckily, I know that one of these lists is empty because we've filled all the way through it. So whatever's remaining has to be the smallest stuff. So I'm actually going to write a separate while loop. And basically, this is going to, like, once one list has been fully inserted, insert whatever is remaining from the other. And I'm going to be a bit lazy. And just check both lists. And I'm just going to have a while loop that says, while if I has not yet fully gone through everything, let's append it. And if J has not fully gone through everything, let's append it. And a good example of what this is doing is if we go to, let's see, 2, 4, 5, 8. Let's imagine we had, let me grab these real quick. Let's imagine I had like 2, 4, 5, 8, 1, 3, actually, let's make this like 20 and 30. And I had like 1, 3, 4, and 5. So if we were using our merge logic here, like we would go through this and we'd add 1, we'd add, and then this would move forward, and then we'd add 2, and this would move forward, and we'd add 3, and this would move forward, and let's just make this 50, and we'd add 4, and this would move forward. Not get curved, but move forward. And we'd add 5. And then, right, J would then equal like length, right? But I still have these guys here that need to get added. But at this point, I know they're all bigger. So at this point, I can just loop through and add those remaining items.
Also, they would already be ordered.
Yes, they would. Thank you so much. Yeah, I was looking at that and I was like, wait a minute. And I'm glad I didn't do it on purpose, but this is a great example of why, like, the fact that these lists are already sorted is critical to how a number of reasons why that's critical in terms of how this algorithm works.
Because now you can just loop through them. You know they're in order and just tack them onto the end. No
Yeah,
comparisons needed because the
exactly.
comparison's already been done.
Exactly. So we would never actually see both of these while loops run. This is just the lazy approach to implementing. Carlos, yes, sir.
Do we need to increment the counters in those last 2 while loops?
We absolutely do. I forgot about that. That's my bad. Thank you. Great call. And then J plus equals 1. Like I said, there's undoubtedly a more elegant way. Like we could check, the elegant way I think would be to check maybe like, which one of these is lesser or something. And we could probably do like a slice, some sort of slice or list append operation. But this works perfectly fine. And we're going to see a recursive implementation of this in a couple days, in like a week or so anyway. So we now have a merge operation working, and kind of going back to our other code where we see where we're breaking everything into sublists. We see that we're using merge right here. And again, just to use the visual aid, like we start by merging sublists of 1. And I end up with like these 4 little sublists of 2. And we're just sort of placing these in our main items array. But now we double the sublist length. And now, right, I'm working with these and these. And we're looping again. And we're calling merge on the bigger sublists. And so on and so forth until we combine them all together.
You would need to return the result at the very end in merge.
Oh yeah, that certainly would help.
I always forget to do that.
Yes, I was about to say, in fact, that I've had many technical interviews where I forgot to return something after implementing all this correctly, and then that threw me for a loop, no pun intended, and kind of I screwed up my performance. So every time I do a technical interview, which has been a while, I make a checklist on a piece of paper of gotchas, and some of the gotchas are always like, make sure I'm returning the values, make sure I'm returning what the problem wants. Sometimes the problem wants the length of a list instead of like the list itself. And now, fingers crossed, we should actually be able to run this. Though it's totally possible. This is a lot of code. I may have a bug here. And in the interest of time, I'm not going to add print statements, though we can actually add, let's do print merge print left and right. And let's see what this looks like when we run it. And then we'll break and do retro, because I realize I ran just a little bit long here.
Uh, in your print statements on 42 and 43, put a comma instead of a plus, I think.
Thank you. Yep, I knew in the back of my head that that might not be how to do it in Python. And I figured I would just run with it and see if it worked or not. There we go. So let's see, what are we printing out? We're printing out our sorted list, which is totally not sorted. Um, so I clearly have some errors in my implementation here. My guess is the error is probably in this copying step, if I had to guess. Um, oh, I also see my right list is empty. That's actually a huge problem. So let's tackle the right list problem and see if that fixes it. And if it doesn't fix it, we'll break and I'll tackle it separately. So let's just print out the left and right sublists. And we know the right sublist is going to be empty, but this might give us some bigger data, some better data. And this is interesting because we're actually it looks like initially this works, but the first or second time after merge is called, something bad happens, and I'm not getting a correct sublist.
Probably something to do with the logic in your line. Oh, never mind. 27, when you make your right sublist, because it looks like you do it right the first two iterations, and then it goes to an empty list. Can you print out right sublist, or at least those values, the slicing values? Because
Yeah,
I plus sublist length, that's going to rapidly explode because you're doubling sublist length, and maybe that's too much.
yeah, yeah. I think
Copy and paste that thing, put it in Chat GPT.
yeah, I think yeah, putting it in Chat GPT is not actually a bad idea. Um, we we do have to stop. Oh yeah, no, go ahead.
I was just gonna say because you have the two times sublist length in your for loop, and you also have your two times your sublist length on line 37. So maybe that's only needs to happen one time, and what you're doing is you're rapidly getting out of the indexes that are involved in the list or something. I don't know. I'd have to stare at it for longer, but that's my thought.
Yeah,
Maybe. I don't know.
yeah. No. I think you're onto something. Let's see, because this slice, it starts at I and it goes to the sublist length. And we want this other slice to start at like one sublist out. Um, and maybe this, yeah, it's definitely something here. And my brain is a little too fried to fix it. Because if like this is right, if we have 1, 2, 3, 4, 5, 6, 7, 8, and our sublist length is 2, our left sublist starts at I, and let's just say for argument's sake, like I is 0, and it's going to go to the sublist length. And so then I want the next one to start here. So I plus sublist length should get us here to start at 3. And I want its length to be 2. So this part feels wrong. It feels like this should be maybe like I plus sublist length times 2. Like that.
I got it to work on mine, Adam, by moving the sublist length doubling outside of the for loop. Because it does that every single time on line 38.
Oh. Oh. Even better kind of error. Right here. This is inside the for loop. Yeah, because I was getting a little confused because I was like, I think that other arithmetic just does the same thing a different way. Yeah, that is almost definitely the issue. That's a good catch. Because we wanted to chunk, and then after it's done chunking, we double the sublist length. The job of this for loop is to chunk stuff. I had this indented and inside there. And so the sublist length was doubling as we were chunking. Let's see if that does it. Yeah, great call. Thank you so much. Yeah, and Nick, I believe it was, thank you as well for helping debug. Yeah, great job, guys. So we're going to see the recursive implementation, which is really how you should do this. It makes this much cleaner. That said, this is a great example of an error that's really easy to make, right? And so in a technical interview, like it's important not to be thrown and to have a process for debugging this kind of stuff. And honestly, you guys did a great job of helping me with that, of myself being on the spot. And this is actually a great example of like how a good technical interview would go. Like in this case, in some ways, where like you guys were the interviewer and I was the interviewee, because we were digging into this, we were laying it out, we were thinking it through and breaking it down and making progress, right? And we got to see the thought process laid out, and then we actually found this other issue. And this is also a great example of how, like, the important thing, yes, it's great to get the code right the first time, but the important thing is that I can show that I understand the algorithm and I know how to debug. Because if I understand the algorithm and I know how to debug and I can like have good back and forth communication with the interviewer, if we find out that this is the issue and the interviewer has confidence that I understand how merge sort works, then that's not the end of the world, right? And in some ways it's a plus because they get to see my process. All right, let's take a break here and let me go ahead and stop the recording and then we'll do